Alright, so today we are going to do this exercise. So let's take a look at what this exercise is all about. We have here a bracket. So this bracket, the material is aluminum alloy 3003, and it has a loading point here, a hook point. You can find this typical bracket probably if you look at any fire extinguisher. So fire extinguisher, they have all these brackets and then they mount on these brackets lah. So let's say we would like to set the safety factor as 1.3, and you need to apply proper boundary condition and load. So the objective of today is we would like to find bolt reaction force, meaning if you put 4 bolts here, 1, 2, 3, 4. So 4 bolts, how much the bolt has to withstand at maximum capacity. So number one, you need to find out lah, berapa, what is the maximum capacity for this bracket lah. So if you would like to do some manual calculation, you can use this particular formula, which is cantilevered beam. So you can test up certain loads lah and see where your deflection goes. So there's no formula for a bracket that looks like this. There's no formula for that lah. There is a formula, however, for a simple cantilever bracket mounted to a wall. So something like this, you can determine the load by checking up what is the deflection maximum. So Vmax meaning how much it deflects lah. Maybe something like that. So this is delta. So you can find out by PL cube over 3EI lah. So you can test it out to make sure whether your analysis is correct or not lah. So this is the things that you can do. So number one, find out what is the load maximum. Number two, number one is load. Number two is bolt forces. So pretty easy. So let's start. Let's go to your SolidWorks, and of course everyone can turn on this one, SolidWorks add-ins, and click on simulation, and give it a while for it to load. And there's another tab that will come out lah, which is simulation. And let's start by creating a new static analysis lah. So new study. So click on static, new study, and then you don't have to use 2D simplification. Just use static one, and then click OK. So far, this is what we have. So number one, let's assign some material on the bracket. If you look at this icon, the icon looks 3D lah. So this is a 3D icon. So let's apply material. The material is aluminum alloy. Look at the codes here. Let's say the aluminum alloy is this one lah, 3003. If you look clearly, this is the material lah. And we have to take note lah of the material properties. So let's say I want to capture this material property like that. So as you work, maybe you wanna put some information lah so that you can remember. So currently this is my material, and if you take note on the yield strength, it is about 41 megapascal. So we do not want to exceed yield strength of 41 megapascal. So since we are setting our safety factor is 1.3, let's do some calculation. So safety factor is equivalent to sigma yield divided by sigma stress lah, stress maximum applied lah, stress that maximum that you get lah. So you got 1.3 here. Sigma yield is 41.3. How do we delete this? Cannot delete. My delete button is not working. Let me erase from here. Eraser. 41.3 megapascal. So the maximum stress that you should get in your model is this much lah. Sigma max is equivalent to, let's calculate, 41.3 divided by 1.3 should not exceed 31.8 megapascal lah. So this is how you determine lah. So make sure your bracket does not exceed 31.8 megapascal. That way you get a safety factor 1.3 lah. So let's keep this in mind. Let's keep this annotation and go back to our analysis. So make sure you click apply and then click on close. So you've got 3003 alloy here. Next couple of things that you need to do is, you don't have any connection for the time being because this is just a simple object, one object. You can apply some fixture to simulate the bolt. So right click, we can create either advanced fixture or you can just click on fix geometry. Just click fix geometry, and let's say I've got 4 bolts, 1, 2, 3, 4. So these 4 holes, I have my bolts. So these 4 holes is not moving at all. It is fixed geometry lah. So this is my boundary condition. So I'm going to click OK. And then I'm going to apply the load lah. So it should be external load. And then let's click on a force. The force I'm applying directly at the hole. So if I click this, and you need to change lah. Don't click normal. You need to click selected direction. The direction is probably something vertical, something like this. So click this line. So you're going to get the arrow like that lah. Afterwards, you can apply some loads lah. So you can give it a trial load. Maybe you want to test it for up about 1000 Newton. 1000 Newton meaning it's about 100 kilo. So let's click on OK. And afterwards, you're pretty much done, except that you need to mesh lah right now. So let's click mesh, create mesh. Currently the default is at the center here. We can click on OK, and it's going to mesh for you. Pretty okay, but let's check lah. The mesh, right click and then you click on details. If you click details here, you're going to see what is the properties of the mesh. I can see here that I am getting about 13,000 nodes. My elements is about 7,716. So maximum aspect ratio is about 4.75 lah. Aspect ratio less than 3, which is 99.5%. So 99.5% of my mesh are quite good. You can even go in details and then click on create mesh plot, and then click on aspect ratio and then click OK. So over here you're going to see which are the area that could be problematic. For example, I have a high point here. I suppose this value is about 4.75 lah. So if you look at theoretical part, if you get something less than 4, it's pretty much okay already lah. However, if you have problems like this and if you want to really fix it, you need to apply something called mesh control lah. You can apply something called mesh control. So right click again on mesh, apply mesh control. So maybe you want to control here. Currently, you can increase lah. Element size increase, or you should decrease lah. Decrease the element size there. So create mesh. And you're going to see clearly at the area where you are putting the mesh control, it will have to find the mesh. So if you plot again your mesh quality, click show, and then you're going to see it disappears lah. You don't have any more problem at that particular area. But then again, 4 to 5 still quite good lah. Anything less than 4 is very good. 4 to 5 is still quite good lah. So this is done, and then you can click run lah. Click run. Anything else I want to do here? Mesh. Advisor. Details. Anything anymore? Right click on statics. Properties. These are the things that you can change lah. For example, you want to define any kind of solver that you want. You need to read a bit about that. Okay, this is pretty much okay, and then click on run. Let's run the analysis. So here I got excessive displacement. Maybe my load is too much. Maybe 1000 Newton is too much. There could be some excessive displacement. However, let's run it first and see what is the results. Where are my problems? So I can see that I'm getting this result. What is my yield strength? Yield strength is about 4.1 E7 or 41 megapascal. Again, let's change this. Edit definition. Change it to one myself is okay. Change it to megapascal. Under advanced option, you can click on chart option and then change to general. Under setting, you can change this one to discrete and click on the mesh. And currently you're getting something like this lah. So if you look here, my yield strength is about 41.4. Currently the highest value that I'm getting is 526. So this is totally way out of line already. So if you want to really explore where is the problem, you can click on something called Design Insight. So if you click on Design Insight, you can drag the slider bar. So this slider bar will explain to you where is the highest stress problem lah. Takes a while to upload lah. So this slider bar, apparently the highest loading point is at the sharp corner here lah. Sharp corner here, and there's a bending. As you apply the load here, you're gonna see a lot of bending stress here. Bending stress, you look closely, right? Top is high, bottom is high. However, in the middle is almost nothing lah, because that is the neutral axis lah of this beam. So at least you got some design insights. So click on cancel. Let's look at the stresses again. Show. A good way to check on your problems, you can double click here. Double click. for example, this one is 526. I want to check it lower, for example 300. So I'm getting somewhere lah. I'm currently understanding the problem. Let's check it even lower. 200. Where is the area which is greater than 200? You can see there. Obviously lah, if you want to check it, make sure it is 41.4. You're going to see a lot of problem lah. A lot of area becomes so red already. So red meaning it is exceeding 41.4 lah. So don't go too low lah. Maybe start at something higher a bit so that you really understand where is the problem. Looking at 200, you can see where you're having problems lah. So something like this. So let's check out where is the highest point. You can right click here and then edit definition, chart option. You can click this one, show max annotation. Maximum is somewhere here, so you don't want to look at here lah. This area is high because you have the constraint over there lah, because you have the bolt. So you have to use some ingenuity lah. Don't read the stress at the bolted area, because this is the area where you fix things, so it has to have a higher stress lah. And of course it even has all these sharp corners, so don't read your stress here. So certain problems you can turn on maximum annotation lah. Certain problems don't. So most likely one of the best area to read is probably at the top here lah. I foresee we are going to have problem here. So let's plot some values lah. Click probe and then let's probe here. Somewhere here 194, 215, 239, 280. So if you go further and further to the end, the stresses is getting higher lah. So it's I would say it would be safe to check the values here lah at 280. This one is at node 7411. So these are the things that you need to watch out lah. So this is the analysis that I do with a 1000 Newton load. So maybe you want to capture this load now. Where do I put it? On a new slide. Put it on a new slide. Okay, so let's do some interpolation. So currently, load that I applied is 1000 Newton. The stress maximum that I get is about 280 megapascal. So if you want to lower down your stress to about 31.8, it should be here lah, 31.8 megapascal. Ini node apa? It's node 7411 node. So how much is X? So in order to find out how much is X, you need to do this multiplication lah. Multiply like this and multiply like this. So you're getting 1000 times 31.8 equivalent to 280x. So X is equivalent to how many Newton? So let's calculate. Times 31.8 divided by 280, you get about 113.6 Newton only. So why are we getting these values? because currently your material model is actually something called linear elastic. Linear elastic material model, meaning your material is actually like this going straight line. Even though in reality, if you were to do a real experiment, your material model will behave somewhat like this, and then it's going to flatten out, it's going to fail somewhere, right? However, that is not linear elastic lah. This is, I suppose this one we call it elastic plastic. Elastic plastic. But that is not how our material is behaving right now. Our material is behaving linear elastic. Meaning, even though your tensile strength is somewhere, how much tensile strength? Tensile strength is about 110 only, right? So over here is about 110, 110. But you are testing, you're getting here already, which is 280. So the material model is behaving linearly. And it's going to behave linearly until to the moon lah, all the way straight line. Because this is our material model lah, linear elastic. So it is okay since we are trying to design our part to become lower lah, lower than the yield strength, the yield stress. Both will behave similar in the linear region, in the elastic region. However, once it gets to plastic region, it will behave differently. So let's try out our analysis, however, putting a new value, which is 113.6. And let's see what happened on node 7411. Escape, keep, and then let's run it again. The analysis, change it to 113.6 and then click on OK. Yeah, correct lah. And then let's run it again. Run the analysis. So if you see here, if I put here 200, I'm getting nothing. So change this one to 100. I'm getting something. So it is safe to change this one to maybe 41.4. So I'm getting some high stress at the regions where you have the bolts. But I believe there won't be any problem like the bolts. This is like this. Why? Because you are constraining it there. So let's check out our node 7411 kan, 7411. Plot tool, probe. Where do you want to probe? Can somewhere here lah. Let's try lah. Maybe here. Node 1628. No, how do you get 7411? That would be... I'm nearing here. 6966. Can I just key in the value? On selected entities, no, add location. By right, I should be able to just key in the nodes. Show node element number. Okay lah, somewhere here. See, I'm getting about 31.5, right? 31.5 megapascal. It is close lah, 6966. Let me print screen again. Is this supposed to be? If I paste here, I gotta make it smaller a bit. Should I post it here? I'm getting 31.5, so I am supposed to be getting 31.8. So this is quite close. So it is safe to say you can really do some sort of interpolation by doing this one. Interpolation, and then you can find out what is the value. So this is what we are doing. And this is the safe way lah to determine what is the maximum loading that this thing can withstand lah. And of course, if you want to eliminate all this high stress area, you need to eliminate these corners lah. And if you want to eliminate this problem with the holes, we can do another thing lah. And if you take a look at your worksheet, you can apply something called a foundation bolt. So foundation bolt eliminates the need for you to put boundary condition at this holes. You can create something called a virtual wall, which that you need to do another plane on the wall, and then put foundation bolts. So if you put foundation bolts here, you can even get a lot of things lah. You can make it like tight fit, you can put the strength of the bolts, and then you can find out what are the forces on the bolts, shear force, axial, and so on lah. However, if you want to do a quick analysis, you might not have a problem by just putting boundary condition lah. So another item that we can check is that we can check on list result force lah. If you click list result force, only 2 points I'm putting my boundary condition. Let me check again. Fixture, no, 4 area. Edit definition, no, 4 areas lah. Okay, let's right click here, click on list result force. You can find out what is the reaction force. For example, I can click on this thing, 1, 2, 3, 4, and I can click update. So these are the reaction forces lah that I have. Print screen. Okay, and then click on new slide. Put it over here. So let's analyze this one. If you can see here, I need to find out what are my axes also. This is important also. This is my axis. So let's check it out. How much force that we put just now? I think it's about 113 kot. 113 Newton. Total force 113 Newton. So if you look here, most of the forces I think should be in the y direction lah. Y direction is about 50.5, y direction is about 50.5, and this one, the bottom ones, it's not very high. It's about 6 Newton only. So the top one is taking most of the y direction forces. Let's take a look at Z. Z, you have this one, 48. X. X is that direction. 34. And of course you've got this resultant. So resultant will be the combination of all these forces lah. F resultant should be fx squared plus fy squared plus fz squared square root. So you can get the resultant lah, total. However, if you can imagine a bolt, a bolt like that, bolted joint. So the majority of the forces is failing due to shear. Shear meaning forces in this direction, which is y. So since our load is very low, it's about 113, so it should be okay. Okay, so what else we can do here? We can under plot tool, you can click on ISO clipping. So click on ISO clipping. ISO clipping is Very good also. You can right this slider, it will automatically update for you lah. Where are the high stress area, high area of about 13.66 ISO is actually constant you can understand where the problem is coming from lah. So you know where to modify your design. So ISO clipping is quite good. What else? Section clipping you can do. Click on section clipping. You can see what's inside your problem lah. For example, like this. I'm looking inside my model. You can do sectional views. X. What else? Probe, of course you know this already. And finally animate lah. You can click on animate. And then it will play out lah your analysis. You're not seeing anything here. Why? I suppose I need to edit definition. And currently it's through scale. So if I click on automatic, it will deform quite severely lah by right. Plot tool, animate. Kind of slow. It should deflect a bit Maybe my displacement is very low Click, check your displacement. It's about 0.7 mm only, very small displacement there. So you don't see how it deforms. Sometimes if you want to see things like this, you can change the deformation scale. For example, I want to change it to user defined 100x. Click on OK. You will bam too severely pula change 50x. This is just for you to understand how the deformation behavior. I guess too much also. 30x. We deform it 30 times more so you can see the animation again lah. This is how it is supposed to deform. You can slow it down. Of course you can save the output file and then so that you understand how it is behaving. So URES, you can check the deflection. So you can cancel this one. So be careful with your deformation scale factor. How much your deformation scale factor should be. If you put through scale, you might not see any difference Least stress results equation. Another one is define factor of safety plot. Define factor of safety plot. You can click. For example, I want to set a factor of safety of 1.3. Click on OK. The rest is okay except for these regions But you know the story already about this. Okay, so for the time being, this is what you need to understand.